real pleasure to be here, of course, and it's a particular pleasure to introduce one of my students that I've learned an awful lot from over the years. I think if I've had a successful career, it's very much dependent upon standing on the shoulders of very bright young men that I've learned a lot from and forgotten a lot. But it's particularly fitting to get into this subject of the Northwest Passage. Warwick Vincent graduated from Auckland University. He's a Kiwi. You know, it's a small country, and only a few great men are allowed to lead because they have to keep up the intellectual power of the country. And Warwick got away at a fairly tender age after completing his undergraduate degree in 1997. No, 1977. And then we were very fortunate competing with many American universities to acquire him at Davis, California, where he completed his PhD in 1977. So, okay, I've got that. Anyway, he got through the undergraduate period really fast. And then he did something really spectacular for a young man. He went off to the Antarctic. And I've been there in 1960 and 61, and my footsteps had long since melted from the snow. And Warwick and several of my other students, including John Priskew, who's a professor at Montana State, Bozeman, Montana, have been working there ever since. In the meantime, Warwick married one of my undergraduate students and learned French and became a distinguished professor at the University of Laval in Canada, not far from Montreal, where we had our a very recent American Society of Limnology and Oceanography meeting where Warwick, of course, starred. In the meantime, his wife took over an icebreaker, literally, and began to ply the northern waters along with Warwick, who has just come back from the Northwest Passage. And when I was a kid, I could read things and remember them, sort of line for line. And when I was reading the book, The Northwest Passage, how many of you read The Northwest Passage? Anyway, for some reason, the preface to that just stuck in my mind like glue. And somehow I feel it just perfectly fits the introduction of Dr. Warwick Vincent, member of the Canadian Royal Society at a very tender age. It goes, on every side of us are men who search perpetually for their own personal Northwest Passage, risking fame, fortune, and life itself in this vain but hopeful quest. But who can say that they are not happier than wiser, duller folk who sit at home and with sour laughs deride the searchers of this fabled thoroughfare, this panacea for the afflictions of the humdrum world. And the reality, the Northwest Passage is now open. Warwick?
Wow, thanks so much for that, Charles. It's wonderful to be here at Lake Tahoe. And in fact, I've just been out the last couple of days on the lake, and we've been working long hours out on the lake and working with samples, and I'm still swaying backwards and forwards. And if you see me moving, it's not you. Don't adjust your glasses. It's at my end. But it's such a beautiful lake. We're out in the middle of the basin, surrounded by those incredible mountains and beautiful water. And it turns out Lake Tahoe still has some really interesting secrets to find out about. And the Tahoe Environmental Research Center is in the process of doing that. And I'd like to take this opportunity to thank so much Jeff Schlatter, director of the center, and all his amazing staff for making the last few days so incredibly productive and also incredibly enjoyable. So thanks so much for that. And of course, it's a real honor to come to Tahoe and to be introduced by Professor Charles R. Goldman, who is my professor. And in fact, I could probably spend the next hours, days, weeks talking about Professor Goldman, because his career is just extraordinary. He has, turns out, I'm not the only person who can say he's my professor. There are about 100 of us. He's trained limnologists who now work on freshwater science, who now work on every continent of planet Earth. There's research going on of Charles's limnological children and grandchildren, and now great-grandchildren in all four corners of the Earth. And it's a real honor to be part of that group. Some really amazing people. Many dozens of postdocs have passed through Charles's laboratory, and he's generated fundamental insights into how lakes work, what happens at the base of food webs, and has promoted Lake Tahoe, in fact, around the world as a place in which you can learn not only about Lake Tahoe, but also about lakes and how to look after fresh waters throughout our planet. And of course, it's been Charles's inspiration and incredible hard work from the 1950s onwards that led to the creation of this beautiful building and beautiful center, the Tahoe Environmental Research Center. So it's a real honor to be here and a great honor to be introduced by my professor.
Thank you.
So I'd like to talk to you about the polar regions, which are my favorite parts of planet Earth. And I wanted to start from where I'm based, which is Laval University, as Charles said, in Quebec City in Canada. And I try to line it up there in Google Earth so that it's the center of the world. But as everyone in this room knows, the real center of the world, if not the center of the universe, is Lake Tahoe. Right? So they got it right in Quebec City. They just got the continent right, just the location they got it correct. So all roads lead to Tahoe. And in my case, my road to Tahoe began in this place here in New Zealand, out in the South Pacific, and it was here. I grew up in Auckland, and it was in New Zealand that I met Charles Goldman for the first time. But I'd actually heard about Charles as an undergraduate, Professor Goldman, and his work in particular because of his work in Antarctica. And that's because Antarctica is a very important place for New Zealanders. It's the continent right next door here. The American program, for example, is based out of McMurdo. So this is about 2,400 miles to the south of New Zealand. The Italian program is based out of New Zealand as well, and then moves on to Antarctica. New Zealand has a long-standing program in Antarctica, so it's an important place. And it's a big place. It's a continent. It's a continent covered by ice, and it is actually 40% larger than the United States. It's a huge area. So if you take a slice through Antarctica, look at it in a cross-section, this is what you see. So here we've got the mountain ranges, amazing mountain ranges going up to over 12,000 feet, 14,000 feet. This ice cap, which is up to a couple of miles thick. And then there were some very special areas right at the edge. And that was of great interest to me, and it was of great interest to Professor Goldman. There's this one area here where this mountain range is like the Rockies, except it's the Rockies that start at sea level and just goes straight up to 14,000 feet. And it acts as a dam, and it keeps back all that ice. And on the other side is a series of ice-free valleys. They're called the dry valleys. It's a polar desert. Amazing place. So here's what it looks like from the other side. Here you've got the Rockies. They're not the Rockies. It's called the Transantarctic Mountain Range. And there are glaciers. On the other side there is this ice cap. And there are glaciers that crash on down here. And then you've got this beautiful look at it. It looks a little like Nevada, actually. A little cool. Average air temperature is minus 20 degrees. And there are glaciers. And the glaciers in summer, they melt up just a little bit. You get hot days getting up to +1, +2 degrees. And the water starts to flow. It's very beautiful, actually. You can hear these glaciers producing the fresh water that's coming down these streams that only last for maybe a few days or a few weeks at most each summer. And then these streams flow into lakes, some of the most extraordinary lakes on planet Earth. These are lakes that are covered by ice throughout the year. So this is a glacier here. This is one of these lakes. It's called Lake Bonny. This is another lake. It's called Lake Vanda. And so this is the middle of summer. So there's up to about 12 feet, 15 feet of ice sitting over these lakes. And the reason I've become very interested in them is that this guy, Professor Charles R. Goldman, who produced a paper in the 1960s that was required reading as undergraduates at that stage, and he talked about these two Antarctic desert lakes, lakes that were permanently capped by ice, and he discovered all these remarkable features underneath the ice. So, like I said, average air temperature minus 20, you got a heat wave maybe of plus 2 degrees in summer, but just under the ice, suddenly temperatures go from 0 and they increase. And the bottom waters here at about, what would that be, about, got a couple of hundred feet, plus 25 degrees. It's hot water on the bottom of these lakes. There's a lot of debate as to why is that? Why could there be that? And Professor Goldman's team, which included David Mason, who was one of his graduate students at that stage, working on Mono Lake. David Mason did the classic work on Mono. It was really the launching off point that led to later work in the creation of the park and the conservation of Mono Lake. And John Hobby, who's a very famous fellow who set up the big Toolik Lake, Alaska long-term ecological research site, very well known throughout the world. And John Hobby, I believe, was your first postdoc. Is that right, John? So it was quite a team that went down there, and they found these remarkable things. Photosynthesis sitting down at the bottom. Well, many years later, I was able to get down there. In fact, soon after finishing up my PhD with Charles Goldman. And with my wife, she was operating undercover in New Zealand at that stage with the name Warwick Vincent. She went back to her original name, her maiden name in Quebec. In Quebec, in fact, the province of Quebec does not allow women to change their maiden names. So you go born with one name, you stay with that. So she was quite happy to go back to Lovejoy. So she's now no longer in deep cover in New Zealand. So that we found that there were these deep layers of phytoplankton, in fact, deep layers of algae, somewhat similar to what we might find in Lake Tahoe. So here we've got all this ice, and then there are layers of algae up near the surface there, and a deep layer. We're interested in the life support system, like the production of nitrate in these waters, what keeps these lakes ticking. And it turns out that not only is there life in the water, under the ice, but there's also life in the ice. And one of my friends and colleagues, and also a former graduate student, Charles Goldman, is working on this. He's been working on this for many years. His name is John Priscu. He's been working on this life actually living inside the ice, between the ice crystals, inside the lake ice. He likes to think of this as an oasis of life in the polar desert. Maybe not an oasis with palm trees, but microscopic. But then it turned out there was another kind of life that we had absolutely no idea of as we were sampling the water. And it became known a little bit in the 80s and then in the 90s, and now is a lot more known. And it came from sending down divers through the ice. So this incredible ice area. So first of all, you have to melt a hole big enough to put a diver through. So that sort of hole, and typically what they do is they use a coil that you pump through a heated solution of glycol, and that spiral gradually makes its way down, so you're dealing with a total of maybe 5 meters, 15 feet, 16 feet, 17 feet of ice, and it takes about 2 or 3 or 4 days for this thing to gradually melt its way through. You're pumping it out. You've got a few days producing the hole, and then you need about 2 weeks to persuade somebody to go down there. That's where the skill comes in. And there is such a character, and he's a good friend, a really good guy. Probably the most experienced polar diver in the world. His name is Dale Anderson. And he likes to dive down through these holes on his own because you're in a tight space there. If you had 2 people, you could get into a lot of trouble with your tanks. And so he dives down on his own to the bottom of these lakes. And he found these incredible communities growing at the bottom of the lakes. It's like an Amazonian jungle down there, layered communities. And in fact, they're pink in color. They're looking like coralline structures. They're pink because they contain this very special light harvesting pigment. It's a protein, actually, that's actually optimized for just absorbing the last little specks of light. And you can imagine, you've got 15 feet of ice, and you've got snow on top of that, and then this long water column. And these are actually the closest analogs we have to stromatolites, the original life forms that occurred on planet Earth 3.5 billion years before the present. And here they are, living here underneath the ice, dreaming of the Precambrian maybe billions of years ago, and totally unimagined. And as a scientist, you really have to be prepared to be humble, because you keep finding things that you had no idea about, and you realize that, boy, it's time to start again and really rethink how these ecosystems are put together. So these are special areas. John Prisco and his colleagues have been examining temperature and photosynthesis, a lot of different processes in these lakes over the last 20 years or so. And he finds that, in fact, in this region of Antarctica, this area is cooling. And now as the data is starting to come in from different places around Antarctica, what we realize is that there's a lot of regional variability. Different parts of Antarctica are behaving in different ways to the overall global warming trend. Of course, it's a huge block of ice. It's the world's largest freezer, but it's heating up in different ways. There are places, like where John is working here, that are cooler, but there are very large areas that are warming up. And there is one area, this is called the Antarctic Peninsula. It's immediately south of South America, and that's heating up at one of the fastest rates on planet Earth. And it's thought that maybe that's interacting with the ozone hole effect. That's one of the reasons that this heating effect is amplified. But it's in that area now that we're starting to see some big changes in Antarctica. And it's instructive because it's helping us understand global warming and its implications in other places, including Lake Tahoe. For example, what is becoming clear within this Antarctic Peninsula area is that there are winners and losers when it comes to climate change. There are certain species, in fact the most common penguin species is called the Adelie penguin. This is actually named by an Antarctic explorer, and he named it after his wife. My wife has always wondered, what I'm going to do there in terms of a name to follow that. So the most common penguin in Antarctica is the Adelie penguin, and you can see its numbers are really dropping off the cliff here, and that is because this is a penguin that needs ice. It uses the ice as a kind of launching off point, as a place to dive off and forage for krill. Whereas another penguin species, the Gentoo penguin, those numbers are actually increasing. This is a species that needs open access to beaches because it builds nests of little pebbles on the beach, and it needs good access. So different species behaving in different ways. There are some species that look to be extremely vulnerable. The beautiful emperor penguins, for example, the largest penguins in Antarctica, very beautiful animals, appear to be especially prone to changes, at least according to the models, of changes in ice conditions. We're now starting to see the evidence coming in of declines in krill stock. These are these little shrimp that enter the food web in Antarctica at all manner of levels. Extremely important for the penguins, for the whales, for the seals indirectly. And we're seeing, as you keep drilling down into the food web, we're now seeing changes at the very base of the food web, particularly in this Antarctic Peninsula area, which is a kind of a window into how the Antarctic may be changing in the future. But one of the greatest concerns that we have in Antarctica is the possibility of invasive species, of new species coming in. And the reason for that is that the flora and the fauna of Antarctica is quite remarkable. There's nothing like it anywhere else in the world. Just one example that I can give you relative to that is the benthic community of Antarctica. So these are the animals that live on the seafloor in Antarctica. And they were first described actually by an American biologist back in 1830. And his name was James Yates. In fact, I think he was from New York City. And he went down, and because it was a dangerous place to go, it's still a dangerous place to go, he went down in the early 1800s and took samples, and he kept seeing these amazing things. He brought them up from the sediments. There were giant sponges, and there were beautiful brittle stars, and sea urchins, and feather stars, incredibly delicate structures, but huge, massive things. Isopods, for example, typically these little animals that normally skate around in the bottom of the sea, typically they are like half a centimeter. Well, down in Antarctica, they were there centimeters and up to several inches in length. And he found these things, which he called sea spiders. And in fact, he named a number of them. This one he called Decalopoda australis. So deca meaning 10, olos meaning perfect, podos meaning feet. 10 perfect feet. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these things were enormous. They were the size of dinner plates. So he came back to the United States, and he tried to publish his work, and he talked to everyone. He said, and there are these giant sea spiders and huge life forms. And people said, right, giant spiders. And in fact, it took 80 years before James Yates's results were accepted. It was just unbelievable. It was so far out of any frame of reference. And now what we realize is that what he was talking about, and what is correct, is that this is a community that has been isolated from the rest of the world for millions of years. In fact, it is thought that the Antarctic began its cooling about 40 million years ago, 40 million years before the present. And by about 35 million years before the present, there was a major collapse of many warm water species. And one of the most important species that collapsed, never to come back actually, was the group of crabs. So crabs that race around on the bottom of the ocean that actually eat these very delicate structures. They're bone-crushing organisms that can disrupt these basic bottom communities. And so for 35 million years, these communities have evolved and have developed without any kind of biological disruption. The crabs are not there, they're not walruses, there are no grey whales of the type that we find up in the Arctic. It's a very special area in terms of biodiversity and these delicate communities that could only survive in these unusual conditions. But it could be changing, because the reason that this area has been so protected from these other entities, and so you're able to get these fragile species, is because of the barrier of temperature. The cold is acting as a filter, preventing the northern species coming down into Antarctica. And there's a great deal of concern about new crab species, larval forms that are starting to turn up. This guy is not there as yet, but there is a lot of concern about regulating boats, for example, at ballast waters. Tourism is very important in Antarctica these days to prevent the introduction of these species. And this is true throughout the world, actually. This is a lesson for all of us, that with climate change, our ecosystems, including Lake Tahoe, will be increasingly sensitive and vulnerable to new species and changing the ecosystems in new ways. So I want to leave Antarctica at this point. As you know, Antarctica is a continent, it's land surrounded by water. We're seeing the first evidence of change in Antarctica in terms of biological communities, in terms of air temperature, in terms of sea ice. But the place where the real action is in terms of climate change right at this minute is at the other end of the world, the Arctic, which is where I conduct most of my work these days. So the Arctic is like a mirror image of Antarctica. It's actually cold ocean surrounded by continent. And one of the reasons that we're interested in climate change, it's a major theme for us within Canada, and within my research group, the group that I direct is called the Centre for Northern Studies, or we're in French Canada, so we call it Centre du Nordique. You can think of it as CEN, C-E-N, rhymes with Zen, or a concept. And this is an inter-university research institute based at Laval, centered at Laval University, involving 10 universities, for about 50 or so professors, with different sorts of specialties relating to the Arctic, the subarctic, snow and ice conditions, low temperature ecosystems. About 200 or so graduate students. We have three primary themes, but each of these themes is related to climate change and environmental change in different ways. One relates to landscapes, to living resources, so we have specialists in permafrost, for example, and snow and ice, hydrology, the flow of water, climatology, people working on landforms, and then biologists working on biodiversity and population dynamics, ecosystem structure. An important approach in our institute, and it's one that's been applied here at Tahoe as well, is to go back into the past to better understand the present and to better predict the future. And so we have different specialists in the area of paleoclimatology, paleoecology, paleolimnology, taking sediment cores and soil cores, ice cores, to better understand what sort of variability there was in the past. One of our sites is here. It's a beautiful lake. It's caused by a meteorite hitting planet Earth about 1.5 million years ago, 1.3 million years ago. What was that date there? 1.3 million years ago. Creating this beautiful circular depression, which was filled with water, and we think that it remained as liquid water even during the last glaciation, sort of like a Lake Vostok analog. And today it's open water. The astronauts like to take pictures of it because it looks like an eyeball looking up at you into space. And in fact, the Inuit, the native communities of the north, refer to it as the crystal eye of the north. But that has a very interesting sediment record that may help us understand a lot more about variability in climate and the Arctic in the past. And then our third theme is really more applied, where we're trying to develop risk assessment strategies for changing climate, new ways of, for example, in terms of managing caribou herds, restoration of plants in areas of degradation associated with mining or military operations in the past, ways of dealing with permafrost that is now melting. Within our centre, we don't have the John LeConte, unfortunately. It's out on this beautiful Tahoe Environmental Research Centre vessel today. But we operate fixed wing and helicopter logistics through part of eastern Canada, and then further to the north, that's operated through a federal agency called Polar Shop. But our helicopters do float, Professor Goldman, so we can actually do limnology. And we run we have a series of climate stations and field stations in eastern Canada. So here we're based in here. This is our secretariat in Quebec City at the biodiversity, and we have these stations dotted up through the subarctic and the Arctic. First of all, we have a series of met stations, and we said, okay, well, what are we going to call these climate stations? We looked at a dictionary in Inuktitut being the language of the Inuit, the Eskimo of the North. We asked, well, what's Inuktitut for climate? And the word we got was Sila. So we called our network of climate stations, about 75 of these, Sila. Well, it turns out, when we talked to the Inuit, which we probably should have done to begin with, they said, actually, Sila is a lot more important than that, because Sila is not only climate, it is all things around us, and it is the link between our consciousness and all things around it. And so it's a very Inuit kind of perspective on the weather and the outdoors and their environment. Actually, a much better name than we could have dreamed up. And then we have the field stations we call Kaucha Savik, which means place of study. So our main fuel station is here. It's right on the edge of Hudson Bay. I was just up there about a week ago. And this is a place in which we're starting to see substantial change relative to air temperature and to ground temperatures. And it's here in this peninsula of Quebec, Labrador, which is this huge peninsula that juts out into icy seas, about twice the size of France. And it's been cold for a long, long period of time. It's sort of a bellwether of change because it's been extremely stable with cold, ice-covered seas in Hudson Bay and the Labrador current coming down here. So if we use this paleo approach and going back into time, taking out a time machine and examining a core of lake sediment or a core of of a swamp sediment. What we see is that, for example, the number of pollen grains is extremely stable for year after year, decade after decade, hundreds of years, millennia. Actually, this is a region that we think has been extremely stable for millennia, thousands of years. But it's changing. And if we now look at the air temperature data, this town actually has 4 names. It's typically Canadian. Right? There's a lot of, very difficult to figure out where you are in Canada because there are so many names for it. So this is the southern limit of the Inuit. So it has an Inuit name, Pujuwarapik, which means Little Great River. And it's the northern limit of the Cree First Nation, and they call it Wakagustwi, which means the place of beluga whales. And we're in French Canada, so of course we have a French name, Costa de l'Oberland, which means the place of whales. And if you look at your airline ticket, it says Great Whale. So you're never quite too sure where you are. But the great thing is we have air temperature data that goes back here, and back in the 1920s, and you can see that it's bouncing around here, but suddenly we get into the 1990s and the last decade, and it's just through the roof. It's extraordinary. This is the this red line. Can you make out the red line? Can you see the red line? Okay. So that red line is actually the NASA estimate of the average planetary warming. So it's the global temperature anomaly. And so last year, 2010, that value was 0.6 degrees Celsius. So the planet, on average, was about 0.6 of a degree warmer than it was during the 20th century. The same value for this place was 7 times higher. So the north is warming so much faster than the rest of the planet. And we're seeing the effects with our eyes. For example, we've got a northernmost movement of the permafrost line that's gone up by about 130 kilometers. Permanently frozen ground is now moving further to the north. The Thor lakes, which we think are very important as a source of methane, is generating. In fact, another well-known student of Charles Goldman, Katie Walter, has been working on the methane production by these lakes in Siberia. And similarly, as in Siberia, we're seeing expansion of these lakes as the permafrost starts to thaw. Different colors, and actually Shohei Watanabe, my student, has been working on the colors of trying to figure out why do you have you've got, let's see, you've got cappuccino, you've got espresso, you've got cafe mocha blueberry. It's all these incredible colors on the tundra. And you need to talk to Shohei to figure out why that is. As these things melt out and generate, and they're expanding. We know that from examining aerial photographs from the 1950s relative to satellite imagery today. They're expanding, they're becoming more important. And we can see in front of our eyes that the tundra is becoming green. The tundra is contracting. People talk about sea ice contracting, but the tundra is contracting. These low grasses and the bushes are moving further northwards. In fact, the terrestrial ecologists even have a name for that. They call it shrubification. Wanting to impress somebody at your next cocktail, you talk about shrubification. But you can see the photographs are clearly different. The landscape is changing with what we think is associated with that is a number of positive feedback mechanisms accelerating that. And we have real problems for infrastructure because so much of our infrastructure in the circumpolar north is predicated on the basis that the substrate, the landscape is solid. And it is solid. It was solid in the past, but unfortunately that solid was H2O. And H2O is another phase that it's moving into. And we're seeing as the ice melts, ice-rich permafrost is melting, our roads are changing configuration. We see the profiles here of temperature. Temperatures are warming. The layer that melts out each year is getting deeper and deeper. We call it the active layer. It's a big concern for us in Canada concerning runways, concerning roading, and also for construction. And in fact, just last week we launched a new program called ADAPT, bringing together a research program, bringing together engineers to work with scientists in the natural sciences as well as the geosciences to really try to figure out strategies to deal with this rapid change that we now have to contend with, to figure out how we're going to protect infrastructure, protect ecosystems, manage our ecosystems under these circumstances of permafrost in rapid transition. And of course, another component that is so important in the north is the native communities of the north, in particular the Inuit communities. And one of the first things you realize when you fly into these villages in the north is that average age is so young. The average age is low 20s. Lots of kids running around. 35% of the Inuit population is younger than 15. And so education is a real problem. The dropout rate is in excess of 90% in high school. So we need to work with these young communities and work towards ways of getting them interested in their environment and working with us towards looking to protecting the environment and helping develop the environment in a sustainable way. And one way towards that in our center, the Center for Northern Studies, has been, we've just opened a science community center, which actually was inspired by this building, using natural woods, emphasis on green technologies like the Turk building here, this beautiful building. So you've got the solar panels, but also, of course, trying to incorporate traditional elements because we're there with First Nations and Inuit communities. And this is a place where we're developing displays to, we hope, enthuse young people, kids from an early age, to stay in school and think about their environment and learn more about their beautiful surroundings. One of the ways we've been doing that is an ecological calendar in the schools, where we ask the school kids to fill in, what was the first day you saw when the antlers fell off the caribou? Obviously, this wouldn't work in a southern school, right? So they're really focused on northern changes in the environment. What was the first day that the tundra turned red? When did the bay suddenly freeze up with ice? And I think this actually could be a very interesting anecdotal record of changes through time, and particularly if we could extend that out into a circumpolar kind of perspective. So the north is changing in temperature much faster than the planetary average. And why is that? Well, there are a variety of feedback processes. The predictions are that it is the northernmost latitudes of the northern hemisphere that will likely see the greatest changes in the future. And already we have considerable evidence of that kind of change. And part of that effect is associated with the feedback. The ice up there on the Arctic Ocean is acting like a giant mirror. It's reflecting ice back into space. That effect is called the albedo effect. It's highly reflective. And of course, as you start melting that ice with rising planetary air temperatures, then more open water is available to absorb that radiation from the sun, build up heat, which then melts more ice, which in turn is resulting in increased heat absorption. So we're moving towards a tipping point in the development of this ice-water continuum and producing large areas of open water, the Hudson Bay area that I just mentioned. And in fact, the Canadian Ice Service has just recently published their data on ice loss in northern Canada. And they have identified that the sector with the greatest ice loss over the last 2 decades is Hudson Bay. And we think it's that sea ice effect that is now influencing terrestrial ecosystems and having an influence on the plants and animals that grow there. So I talked a little about this area where our main field station is, but we've got the field stations dotted all the way up. But the place I really like is up here at the very top of Canada. And so I work up there each year. In fact, I think each year I've been moving further north. I think I'm still looking for Antarctica. And finally got to the edge of Canada. And in fact, there are many aspects of the landscape up there that are reminiscent of Antarctica. Air temperatures are very similar in some respects. And we work in a place, we have a little we have a little laboratory up there, a place called Ward Hunt Island Observatory, where we have met stations and different monitoring systems, some beautiful lakes. It's in a park, a national park called Katina Park, which in Inuktitut means top of the world. And when you're right at the northern limit of North America, and you really do feel like you're sitting on the top of the world, at latitude 83 degrees. And one of the things that we're very interested in is the microbiology, as we were down in Antarctica. What's the microscopic life that could exist in these different sorts of ecosystems? And it used to be in the past we had very few ways. When I was doing my PhD thesis here on Lake Tahoe, there were very few methods available to examine that. But now there are new techniques based on DNA and RNA, nucleic acids, and suddenly this galaxy of life is opening up. And we realize that, in fact, most of the life on planet Earth is invisible. We just didn't know it was there. But now we can pull back the curtain and kind of peer behind the curtain, and it is absolutely extraordinary what we're seeing in terms of diversity. And not only diversity in terms of species, but functional diversity. Diversity in terms of the life support systems of planet Earth. And we're also reminding ourselves how ignorant we are, that we know very little about this in terms of how our planetary system operates at a biological level. So we work on a number of extreme environments, glaciers and ice-capped lakes up there in that northern coastline, examining many of these life forms, the way in which they form different layers down through the lakes, and trying to understand what are the limits to life on planet Earth. How do these organisms survive these environmental extremes, and how might they change in the future? There are ice shelves, for example, that occur along the northern coastline. And these are very thick layers of ice. I think they formed many thousands of years ago. They're up to 100 meters thick, floating on the ocean. They're attached to land, so it's land-fast ice. And this is the oldest ice in the Arctic basin, floating in the sea, ice shelves. We're using a variety of techniques, including pyrosequencing techniques to examine the DNA. And we're starting to see big changes in this area. In terms of temperature, for example, this is a place where typically it's like Antarctica. Temperatures are supposed to be around about +2 degrees, +5 degrees. But we're seeing temperatures get up to 10 degrees in the soil. A couple of years ago we measured temperatures up to 20 degrees. Extraordinary. And that's a warm day even at Tahoe. And yet this is the coldest place in North America. And you can imagine the implications of that, 20 degrees Celsius. You can imagine the implications of this whole structure, this whole landscape is based on ice. So you bring up to those high temperatures, everything is falling apart around you. This is a lake that we work on. It's similar to the lake that Charles Goldman worked on back in the 1960s in Antarctica, but this is on the other side of the planet up in the Arctic. And typically this is what the lake would look like in summer, capped by ice as in Antarctica. And in 2008, it lost its ice cover completely. Now imagine that effect in the dry valleys, which may not be that far away. In fact, I think my graduate students were the first human beings to actually be able to row across this lake. This is one of the ice shelves. It's called the Markham Ice Shelf. It's on all the maps of Canada. That's Cape Meares in the background there. And we went out there in 2007 in the International Polar Year to again examine some of this extreme life and try to understand its adaptation to the severe polar environment. We set up our experiments, came back the next year, it had gone. This is an ice shelf that's been around, we think, maybe for 4,000 years. This is the Warhunt Island here, where we set up our camp each year, where our little lab is based. And this is our drinking water supply. It's called the Tinnapark Lagoon. It's nice. This is all ice around here. It's beautiful, fresh water that we're able to use as a drinking water supply. And salinities, if you look at the salinity, here it is, typically good low salinity. Later on that season, suddenly it breached and now it's salt water, which creates a few logistic problems for us, for sure. But it also indicates the magnitude of changes that are taking place. And these ice shelves seem to be going through their final death throes right at the moment, accelerating over the period from about 2000 to the present. The last few years we've seen cracks throughout these ice shelves. This is a series of satellite images that my former student Derek Mueller put together for 2008, and what you're seeing here is over a 24-hour period. This ice shelf, about 100 square kilometers, is breaking up. About 3 billion tons of ice is breaking off and disappearing into the Arctic Ocean. And in fact, this year, we think the ice loss was even more severe than in 2008. We're just trying to put together the data on that right at the moment. And it's consistent with the general trends of ice in the Arctic Ocean. To date, people have really focused on the ice extent. You might see in the newspaper from time to time how much ice is left in terms of aerial extent. But really, the key aspect of the ice that's important is how thick the ice is. Because it's the thick ice that's really been like the cold in the bank that's been keeping the planet at that lower temperatures. And so you can have a warm year, but there's enough ice there in the freezer to keep things at a reasonable kind of temperature. So back in the 1990s, this is how much thick ice, ancient ice we have, or old ice, that we have in the Arctic basin. This is thick ice, multi-year ice that's been around for at least 10 years or so. It was of the order of about 8 million square kilometers. It's a huge area. Now if we fast forward to the last few years, we've essentially lost cold in the bank. We've lost that buffer capacity on planet Earth. We're now right at that brink of the tipping point where we could very easily lose the entire sea ice in a very short period of time. We've lost the buffer capacity. And that's of concern to us because there are so many specialist organisms, specialist animals and plants on land that depend upon that ice and that low temperature for their existence. And these specialists, of course, they include polar bears, they include seals, certain whale species like narwhals. There are certain species that very much depend upon the algae that grows within the ice. And that those algae then they fall down, they sink down through the water column, they help the animals on the bottom, like the different shellfish down the bottom, develop their communities. And for species such as walrus, the ice is important as a platform to allow them to dive on and dive down to the bottom of sediments and meet those shellfish. And it's also important as a source of carbon and energy for those bottom communities. And already we're starting to see shifts in different places. For example, in the northern Bering Sea, there is evidence of a decline in walruses, a shift in the community more to an offshore community and less of a dependence upon these bottom-dwelling organisms. There is a decline in polar bears in certain areas. In other areas, polar bears are actually stable or going up. There's a lot of variability, and of course that creates a lot of confusion in the public mind as well, in terms of, well, climate warming, how can we see certain populations of polar bears increasing? There's a lot of variability. And what it indicates is that we really have to be looking very carefully towards protecting certain areas. In fact, the United States is really ahead of Canada that's declared polar bears as an endangered species. That's very difficult for us to do in Canada because it is a traditional hunting source for the Inuit, and it's also an important element of the ecotourism trade in Canada. So I think it's classified as a lower level of threat in Canada, but it's one species that needs to be looked at very carefully in the future. And then there is this concern about now with the loss of this cold front, a new species coming on in from the south. And even at the bottom of the food web, we're now starting to see changes. The ice is melting, so the Arctic Ocean is becoming fresher. And as a result of that, the cells at the base of the food web are becoming smaller. And we think maybe something similar is going on in Lake Tahoe. We've had the Tahoe Environmental Research Center has had some very interesting data suggesting some plankton changes that are taking place right at the moment. So there might be something in our way that's taking place. So if we take the broad overview there, in both polar regions now, we're seeing evidence of substantial change. We're beyond the point of debating whether or not things are changing. Visually, we're seeing changes in populations of plants and animals and shifts in parallel with the large changes in air temperature. We're seeing the greatest changes in air temperature on planet Earth taking place in the polar region as the models predict, and we're seeing the acceleration of climate-related effects. We're really at a critical time in terms of cultural diversity, in terms of Inuit communities of the north and their traditional resources, and biodiversity. And we really have to think about what can we do to slow down this process. It's a critical time for controlling of alien species, as you're doing in the Tahoe Basin. Alien species, exotic species, invasive species are going to become more of a threat as temperatures increase and increasing temperatures is required. It's a time when conservation is really critical in terms of developing parks and identifying areas to reduce some of those other stresses that work in tandem with climate change. To examine refugia for polar bears, for example. What are areas of the Arctic that we really have to protect to the maximum to allow some of these specialist organisms to survive? So those are all adaptation strategies. Of course, we also have to work in the long term to figure out a way to reduce our greenhouse gas emissions. Some of these effects are now unstoppable, but we need to slow down this process because the end point that we're pushing ourselves towards is not the place we want to be as our species. So we want to try to continue to be on the winning side of the equation. We have a lot of work to do now. So I think I'll leave it at that. Thanks very much.